Understanding just how horizontal movement of the Earth's surface might topple over a rigid object is a bit more complicated than it might first seem. One point is that distance does matter. In order to make a rigid object like this topple over, the center of mass does have to move horizontally with respect to the base, and in the process of tipping, the center of mass also has to rise. The fact that the center of mass rises means that the gravitational potential energy of the object increases, and that might involve some exchanges with kinetic energy or with work done by the surface below. It's also essential that force and acceleration become involved in this. It's not going to start tipping unless there is some reason to make it start tipping, and that does require an analysis of the forces that are involved. For the object that we're using, we know the total height, we know the diameter of the base, and we know the diameter of the ring, which is there largely just so we have a place where we can apply force, and we also know the total mass. Since the object is symmetrical, we know that the center of mass is located at the geometric center, and we're also placing our object on high friction sandpaper to keep it from slipping. Using torque, we can calculate the required horizontal force at the ring to initiate the tipping process, and the value we got is 0.046 newtons. Invite everyone to repeat the calculation and check and see if that's correct. We calculated from the geometry that it has to reach an angle of 13.6 degrees away from the vertical before gravity will continue pulling the object over, and that the extra gravitational potential energy at that tipping point will be 0.14 millijoules. We can check out the tipping process by using a force probe to push the object over at slow constant speed. The data verifies our calculation that we need a force of about 0.046 newtons to initiate the tipping. It's also interesting that the force needed decreases as the object moves away from its equilibrium, since the torque provided by gravity decreases. This is very different from the way restoring forces increase with displacement for a pendulum or Hooke's law spring. If we replace time with displacement on the horizontal axis, we can also integrate to estimate the work done in reaching the tipping point. The measured work is 0.19 millijoules, and that's 35% greater than the value of 0.14 joules we calculated, perhaps because of friction as the probe slides against the ring. From the perspective of an earthquake engineer, the question may be, how intense an earthquake can our object actually survive without tipping? Reconciling the physics with that requirement is not trivial, but it turns out that Newton's second law does provide a rather simple answer. The acceleration that we would calculate using our tipping force and the mass of the object is the same as the maximum ground acceleration, which can occur without rotation. And for our object, that amounts to about 24% of g, which certainly does occur for a number of moderate earthquakes. It's important to realize, however, that this is the acceleration that would initiate the tipping process. And that's not at all the same thing as toppling the object. If the acceleration occurs only briefly, as often happens during moderate earthquakes, the object will begin to tip, rise up on one edge, but unless the acceleration lasts long enough or the object somehow requires enough energy to go beyond its point of no return, gravity will restore the object to its original upright position.